All right, folks. So let's start discussion on deadlock management, and feel free to ask any question if you have. Okay, the resources are from where I have read and taken some points are the following. Mainly these two books I have followed for this one: Silver Shards and Herbert and Tenenbaum. Okay, you can read it from any book. Exactly same contents are there in most of the books. Okay, all right. So we have studied this in the last class. Okay. There are four necessary conditions for deadlock to occur. Bounded resources, no preemption. Okay. Wait while holding and circular waiting. All right. So many books don't talk of necessary condition and sufficient condition. Okay, and however, the places where they don't mention the necessary and sufficient condition, which is the most of the places, essentially they assume that there is only one resource of one type. Okay, so now that simplifies the problem. All right, so we'll look at the this concept and try to work on try to look at these four conditions and see how we can apply this in case of avoiding deadlocks. All right, and then we have seen we can create the graph theoretical model, okay, by representing threads or process as a circle or node, and then we can also have resources as a rectangle. And then we have two types of arrows. One is for request, and second is for assignment. So you can see the direction of arrow and can find out the request edge or assignment edge. So the one which is here, which goes from resource to thread, is actually assignment. It means the resource here R2 is assigned to thread T3 and so on. And whenever in a rectangle we see multiple dots, it means that each dot represents a unit or of that resource, right? So here there are three dots. It means that there are three resources of type R4. So this is the graph, and based on this we can find out whether system is in deadlock state or not. Okay, so for example, here it is in deadlock state, wherein at this place is not in deadlock state. Right? So this is what we studied. This another diagram. Some places you find diagram in this way, that basically same thing. Edge that is going from resource to thread is directed in this way, from resource to thread. It means that this resource is owned by thread T0, and if thread T0 wants something, then there is a arrow or edge going out. Okay, for a resource, it means that now thread T0 is waiting for resource Y. So we know this diagram, and then we have looked also at this diagram wherein we have multiple units of resources, and then wherein note that thread 0 and thread 2 are in kind of circular wait. Okay, wherein thread 1 is holding a resource of type X. Okay, so when it at this instant of time when thread 1 is holding this resource of type X, we can see that all four conditions are satisfied. Okay, while the system is not in deadlock state. Okay, so these are corner cases. This reason we say conditions are necessary. These four conditions are necessary for deadlock type, but not sufficient conditions. So there are some cases, right? Similarly, yesterday you asked this question. So this, considering this diagram, it is in deadlock. Okay, now you will get the same graph if we put another resource here. Okay, as in this case, right? So now the graph and all conditions remain the same. There's another copy of this node is now held by say process P4. Okay, so but is it in deadlock? No, it is not in deadlock, because the moment this releases, the resource available which can be taken up by P2 and so on. Okay, so that's the reason we say that these conditions necessary but not always sufficient. So there may always be cases wherein these conditions satisfied, yet system is not in deadlock state. So however, for our discussion, let's assume right now that if these four conditions satisfied, then it has to be in deadlock state until unless there is more information available. All right, any question? So if you consider only one copy of the resource and create a graph, and these four conditions satisfied, it has to be in deadlock state. So that's the information that you have. You please remember this. Okay, all right. So today we'll study these three approaches in very short. What are different approaches of handling deadlock? And then one of that is deadlock avoidance. How can we avoid deadlock? Okay, and then we'll look at one algorithm, which is very simple algorithm called Banker's algorithm. We'll try to finish early today. Okay, any question up to this point or in last class discussion? No? All right. So here is one example. How do we handle deadlock? Okay, what do we need to do now in this situation? Okay, all right, so we'll come to this example. So with this, we have studied yesterday as well. Does the deadlock disappear of its own? No. Once deadlock has happened, something needs to be done about it. Okay, like we have assumed, one of the four conditions is preemption. No preemption, right? It means that deadlock, once resource acquired, cannot be released by process. Okay, so so until something is done, maybe releasing a resource or killing some process, etc., deadlock will not go of its own. Okay, and can we say that system at certain point is not in deadlock? Then at next instant or after a few instants, it will never be in deadlock. Okay, so there's no deadlock at time t. Can we say that it will not be in deadlock at time t plus 1? Can anyone tell me?
Sir, it's not guaranteed.
Yeah, it is not guaranteed, right? All right, good. So now there are ways to handle deadlocks are ignore the problem. Okay, how you design your system well? Design algorithm when you're a programmer, you write program such that it does not get in deadlock state. How do you do it? If you're writing multi-threaded program or using multiple processes, and then they are also requesting a shared resource or lock and so on and so forth, then make sure that deadlock conditions are not met. That's one way. Okay, so and then OS will also do something to let system remain in the state which are not leading to deadlocks. Okay, and now this is followed by Linux and Windows and maybe a few other operating systems, because this is simplest scheme, right? Because deadlock detection and so on and so forth could be and recovering for it could be very expensive. Okay,
Sir, could we assign like priorities for resource allocation also? That way, like the condition of deadlock can be ignored.
You think about it.
Yes.
Think about it. Maybe you come hit upon a new solution, right? Think about this. There is always number of ways to avoid deadlocks. Okay, and OS can do, and of course priorities are there, right? In Linux processes, and OS sets priorities, and user can also set priorities. So priorities are always there, but deadlock still can happen between processes of the similar priority. Okay, and we are assuming. See, we are assuming here use of CPU when we say processes in general. Okay, and this is preemptive one. Note that deadlocks usually happens and this is no preemption. It means that once you have picked up a chopstick, you will not put it back, or you will not stop eating. Okay, if you stop eating, say I withdraw because there is not enough chopsticks available, then problem is solved. There won't be deadlock, right? So deadlocks, in order deadlocks to happen, we assume there is no preemption. Once something has been acquired, it has to complete. All right. So just think about it, but it's not as simple as that, because when we are assuming prioritization, then again there can be many processes of same priority, and secondly, you know, the resources, maybe third resource, maybe printer, etc. They are, which is non-shared resource and which cannot be preempted halfway, can lead to deadlocks. Okay, think about it. All right, good thinking though. Okay, so and secondly, we can use protocols to avoid deadlocks or prevent deadlocks, ensuring the system will never enter into deadlock state. Okay, it means that a priori we should know something, and then we have to remain in kind of safe states. Okay, we'll look at this. Okay, and third is, of course, it enters into deadlock state. Okay, then detect it and recover from it, because once it has entered into deadlock state, something must be done. Okay, all right. So these, in different systems, these three approaches are used in many ways, right? So we'll look at. We will not look at this. Okay, I will ask. I will rather suggest you to read about Linux in general, about Linux deadlock, how Linux handles deadlock. So what you said here in just one sentence is not usually the way it is implemented. It could be very different from what is mentioned here. So it must be doing something about it. So it must also be doing something to avoid deadlocks. And what is the way to design OS such that it remains in kind of non-deadlock state? Okay. How should we deal with the deadlocks? First is avoid. Okay. Second is, okay, avoidance is that right in the beginning you should know that what are your needs, and then if system or is going into by requesting more resources, etc., system is getting into deadlock state, avoid that. Okay, so basically it's a dynamic mechanism wherein dynamically delay resource requests so deadlock doesn't happen. Okay, but for that, thread must have enough information about resource requests and use during the timeline. It means that thread or process should know what is its need all throughout its timeline. Okay, say for example, a thread may need 1 MB of memory in the beginning, may need 10 MB of memory at the end. Okay, so this during the lifetime, what is really need and what is the maximum need, that information should be available. Okay, So based on that, if OS knows that granting these resources to a thread may lead into deadlock situation, then OS will delay granting of those resources. Okay. And second is, of course, deadlock prevention. That is, write a code in such a way that it's not prone to deadlock. And third, of course, is when deadlock happens, recover from it. Okay, these three are based on what points we have discussed earlier. Okay, this point we have already discussed. One algorithm you will find in many books is called ostrich algorithm. Is that like, the ostrich? You would have heard about ostrich, right? When ostrich sees any danger, then it hides its head into sand, right? It doesn't want, even if danger is there, it will not do anything. It will just pretend that it doesn't know anything, right? So it's called deadlock denial. So many OS can be designed so that it's not bothered about deadlock, etc., right? So hopefully deadlock doesn't happen. Well, I mean, many OS do follow this method. So coming back to this diagram, so what should we do to avoid deadlock here? Any one of these, when they are coming to intersection where this happens, they should see that this situation is going to happen. For example, this guy will not come to the this position. Okay, so anticipate. Okay, and then if you are seeing danger is happening or deadlock is going to happen, then just back off or do something. Okay, all right. So never get into situation that it will lead to deadlock. This is the simplest way of avoiding a deadlock. All right. So now based on this, we can have, and of course it will lead to our discussion on Banker's algorithm. When a thread requests a resource, OS checks if it would result into deadlock. All right. And if not, then grant the resource right away. And if OS thinks that it may lead into deadlock, okay, wait for other threads to release the resources and then give resources to this thread. Basically, hold the thread that's asking for resources for some time until resources are available from other threads. Okay, so this is one solution that works most of the time, but it doesn't work all the time. Okay, so it means that now at every instant we are taking this decision, and sometimes it may still not work. And this is the example. Okay, this is the one which you studied in last class. So thread A wants to acquire lock X, thread B wants to acquire lock Y, then thread A wants to acquire lock Y, and thread B wants to acquire lock X. So let's see that how does it work. So it's like this, that thread A has acquired lock X, lock Y is available, so thread B also acquired lock Y. Now at this point, it will now execute this. And now this lock is held by Y. So as a result of that, this blocks and this also blocks, right? And then we know that it's too late to take a decision now. What is the catch here?
So thread A will go to sleep.
Yeah. So both will go to sleep because both are in deadlock, right?
Yes.
So now ideally we should execute this. How will we not execute it? Because until we execute it, we'll not know what it is like. So a priori, if we have idea, if the OS knows that thread A will require lock Y, then it will not execute. Right? That's the point we are making. So a priori information should be available. Okay. All right. So additional a priori information is necessary, and it's quite simple method then, that let each process declare the maximum number of resources of each type it may need, and based on that information it can take a decision. Okay. Okay. And dynamically examine resource allocation state to ensure that there can never be circular wait condition. So these all three conditions comes out of common sense. Okay. So now let's look at what are different states that system can be. Okay. First is safe state, where system is into where chances of deadlock is 0. Okay. However, from safe state, okay, when more resources are required, then it should be allocated such that it does not go into something called unsafe state. Okay. So unsafe states are, of course, non-safe states, but there is no deadlock yet. It can lead to deadlock under certain request patterns. Okay. Okay. So thread can request resources in a pattern that can unavoidably leads to deadlock. So once system goes to unsafe state, it does not mean that it is in deadlock state, but some unsafe states can be deadlock states. Okay, so it means that now in unsafe state, if certain request patterns are done, then it can lead it into unsafe deadlock state. And also from unsafe state, it can come back to safe state also. Deadlock state is where deadlock exists. Okay, so we can see that we can actually go into details. When a process requests an available resource, system must decide if immediate allocation leaves the state in safe state or not. Okay, if allocation is permitted, so OS will give the resource only if thread remains in safe state. Okay. Now next question is that what is a safe state then? How do you define safe state? Safe state is a state if there exists a sequence, some sequence, P1, P2, P3 up to Pn. Now note that this P1, P2, etc. are just some index or some name to process, right? It could be any sequence. Okay, it could be P2, P1 or whatever. So for just for our explanation, we are saying that there is a sequence of processes in the system such that for each PI, each process say PI, the resource that PI can still request is satisfied by currently available resources plus resources held by Pj, which j is less than I. What does it mean? Okay, we'll look at it, right? So its meaning is that if PI resources need, okay, if PI resource needs are not immediately available, let's assume that there's a process, we consider process PI. Okay, it needs are not immediately available, then PI cannot wait until then PI can wait until Pj has finished. Okay, and when Pj has finished, then these resources can be taken by PI and it can execute and then complete and return the resources. Then the next process can continue from there. So when Pj terminates, PI terminates, PI1 can obtain the needed resources and so on. So we have to find a sequence such that resources held by other process, plus the available resources is sufficient to meet the need of that process. Okay, then we can say it's in safe state if any such sequence exists. And if no such sequence, note that this is just one sequence we have said here, right? So OS will look at any such sequence exists, then it will give resource only to the process which can release resources such that need of other processes can be met in a sequence. Okay, if no such sequence exists, then system is said to be unsafe. Are you able to get it?
Yes, sir.
Okay, let's
Yes,
look
sir.
at example, then it will become very clear. Before that, these are obvious things, right? If a system is in safe state, then obviously no deadlock. If a system is in unsafe state, then there is a possibility of a deadlock. Now, in order to avoid deadlock, we must ensure that system will never enter into unsafe state, because if it enters unsafe state, there is a chances of it getting into deadlock state. Okay, so deadlock state is unsafe state, but not all unsafe states are in deadlocks. Are deadlock states, but unsafe state may lead to a deadlock state. So as long as the state is safe, OS must avoid getting into unsafe state. Now it will become clear to you once you see this diagram. These are safe state shown in green. These are all unsafe states, and there are some deadlock states. Okay, here. Okay, so system can remain in safe state, then absolutely no issue. It can get into unsafe state, can come back to safe state, but this transition should be avoided because it can finally lead into going to deadlock state. All right, so there's the theory. Now, when we are granting resources to any thread, okay, when OS is granting resources to any thread, it must see that it is getting into unsafe state or not. If it is getting into unsafe, then it can delay granting of resources until resources become available. That's the theory. Okay, all right, any question? All right, pictorially, once we see it now, that becomes much clear. The concepts become much easily understandable. All right, so here is example. Now we are taking little older example when tape drives were used. You know, like hard, like disk drive, there used to be tape drives, right? Still many companies use tape drives because tape drives can store huge amount of data. In my previous company, we bought tape drives because we used to back up the whole system every day. Okay, for disaster recovery mechanism, as a disaster recovery mechanism, right? So tape drives are still in use. So information goes into tape, and there's a drive, a mechanism of using tape, that's called tape drive. Okay, so there are three processes: P0, P1, and P2. And note that these are non-shareable, right? In the sense, non-shareable means that non-preemptible. Okay, and then one tape cannot be, when it is in use by one process, it cannot be used by another process, right? So that's the reason we may say it's non-shareable at that time. Okay, now maximum need of P0 is 10, and this is at some instant of time. This is the current usage, which is 5. It means that it may ask for 5 extra resources, 5 extra tape drives, right? So P0 maximum need is 4, currently is holding 2. It means that it may ask for 2 at certain point in time. P2 is holding 9. P2 needs maximum, it may need 9, but it's holding 2, so it means the 7 more. So now current usage is 5 plus 2 plus 2, that's 9, and total we have 12, so still 3 drives remain. Okay, simple. Okay, all right, so now what is that sequence then? Okay, what is that sequence that OS will grant into. So there can be many sequences, there are 3, so we can first grant request to P0, then P1, then P2. It can do it in any order because they all may need this many, right? Let's assume that they are going to ask this many, then in what order it must honor the request, right? So the other sequence could be P1, P0, P2, and so on. Number of combinations, right?
Sir, I have a doubt.
Yeah.
Sir, couldn't we say unsafe state? Like currently, they are working fine. But if all three process 0, 1, and 2 ask for more resources, then there can be a possibility of deadlock.
Yes, they are asking it right now. Let's assume that this is an instant time t, and at time t plus 1 they are asking for these ones. Okay, all right. So the answer is, of course, P1, P0, P2. You are right. This is the correct answer. And if you do it, say any other one, say P1, P2, P0, then what will happen? First, you give it to P1, then 3. Fine, this will be done. So basically, then P2, then oh, so it will require 7 here. So this will get into deadlock. So you're right. So only this sequence will give us, is a safe sequence. Okay, all right. So now out of all these combinations, the method that we are trying to come out with is, out of all these sequence, there exists a sequence which we
Sir, but yes, sir. But in case of P1, P2, P0, like we can wait for the P1 to finish and then allocate remaining resources to P2.
yeah. So even then, okay. So
Sir,
right now,
like
how many will be? Just look at. I mean, does it answer? Okay, let's look at it. Let's see. Okay, you mean to say is that what was the sequence you said? P1,
so P1, P2, and P0.
P2, P0. Okay, what will happen? So P1 you give
Yes, sir. Like
2, so remaining is 1, and then here we'll have 2 plus 2, 4. Okay, so it will do its job. It will
yes,
release
sir.
this 4.
Yeah,
It will release this 4.
yeah,
Okay, and then it will have 1. We have already have 1. So 4 plus 1 is equal to 5. So 5 resources you give it to it. How many it needs?
oh, yes, yes, sir. Sorry.
Yeah, it needs 7. No? That's fine.
Yes.
The max, max need is 9. So this is what extra it needs, right? So so we know that's in deadlock then. All right. So now the point we are trying to emphasize is, there exists a sequence such that, by using that particular sequence, in which the previously held resources will be released, such that the need of other process can be met. Okay, so it means that P1 can complete with current resources, right? So here, and then now P0 can complete with current plus P1, because P1 has now released resources, and P2 can complete with current and P0 plus P1's resources. All right. So let's take another example, and you tell me whether this is a safe state or not. Now here I have taken out this one, because this obviously from this you can make out what it could ask for. So process ABC, A has resource 3, B has 2, and C has 2, and free are 3. So the number of resources are 5 plus 7 plus 3, that's equal to 10. You tell me this is safe or not safe?
Not safe.
What is how does it lead to safety? What is the sequence? Here is the sequence, right? First granted to B, so it meets the need of this one, okay, and then 4 are available. 4 plus 1, 5 are available. These 4 are released from here, is 1 is here. So then granted to C. So it will then it will get all 7. It will also release, and then finally, this can execute. All right. Any question? All right. How about this one? Is it safe?
No.
All right. So there is no such sequence that can lead us to pardon? Okay, so basically at this point, then you can see only here you can meet the requirement. So that's what it has done here. After that, 4 are freed up. Okay, so 4 are freed up. Now both of these need at least 5. Okay, so it means that it's not. All right. So now let's, based on this, you already have come to this algorithm called banker's algorithm. Okay, how does a banker do its job? So have you heard a big story in newspaper sometime back last year around March, April time, wherein one mutual fund company, which is a debt mutual fund company, said that it's freezing the account and it will not honor the request of redemption. Have you heard of this? It happened rarely. Okay, there's a company called Franklin Templeton. Okay, unfortunately, I have also put in my money there. Okay, in March or April, sometimes soon after Corona, out of all mutual fund companies in India, they say that they cannot meet the redemption request or request to withdraw money out of the mutual fund. Why did this happen? So there was, of course, news in newspaper a few days back earlier that there is a heavy redemption happening in this mutual fund, and as a result of that, everyone start withdrawing. Okay, when everyone withdraws money, then of course they don't have the money to give to everyone. Okay, all right. Similarly, it may happen with credit card company, right? So you have a credit card and your credit limit is, for example, 1 lakh. Okay, and but you're not withdrawing, and of course the money held by credit companies is limited, say 10 lakhs, but it will give 1 lakh credit limit to say 100 people. Okay, what happens if all 100 start withdrawing? Then they will never meet the demand, right? They look at the average what you will in general need money, right? So my credit limit could be 1 lakh, but I may need say 10,000 rupees, and at the end of month I can pay that back. Okay, so they know that money will come at the end of month, and so they can meet the requirements. Okay, so now let's look at this algorithm. Similarly, a banker has limited amount of money. Okay, it will say that to different customers that what is your maximum need, state your maximum need. Okay, but it knows that very rarely somebody will ask for maximum need, and then it should have, but some may ask. Okay, and it should have enough money to give that person or that process what it needs, and it knows that the end of month or end of a period it will get the money back and it can honor. So if many people ask for the money, then it will look only for the one whose request can be met and will return the money. All right. So this is a simple banker's algorithm. Okay. So this algorithm says we need to know the worst case resource need of processes in advance. So every process has to say what is the maximum amount of resources it wants. Okay, let's assume right now resource is only one type. It's like knowing the credit limits on your credit card. Okay. And then suppose you give some processes or maybe a process, one process, all that they want. Okay, such that it can execute to completion. And then the money or the resources will come back and honor the request of others. So just give it to the one whose job can be completed and you get the resources back. Okay. All right. So this is a very simple algorithm. So the process declares its worst case needs and then it asks for what it really wants. Not necessarily everything it may want, because the maximum need is specified. And then based on that requirement, okay, the algorithm decide when to grant the request or when to give the money, all right, or resource. And it delays the request or there's a granting the resources, okay, unless it can find a sequence of processes such that it could grant the outstanding needs, their outstanding needs, so that they can terminate and letting it collect the resources and then give it. And in this way, it can execute everything in completion. This is exactly what we have done earlier in the example, right? So what is the process? Okay, everyone has to tell, every process tell how many resources they need. Okay, and then before meeting the further demand, so it will grant the resources based on that or in such a way such that that request that's granted resources will return it or maximum resources for that process it can grant and it will return it, and then based on that it can give it resources to other process. All right. So algorithm checks to see if the granting a request lead to unsafe state. If so, request is denied. Okay, if banker gives too much money to a process and that still needs further money, then it's not going to be helpful because system is getting into unsafe state. So if granting a request leads to safe state, is carried out. All right. Example is very simple that there are number of customers, it wants to give only to few. Let's take the example here. There are 4 customers A, B, C, D. These are shown here. Okay, and their overall their needs are as follows. It needs 6 units. Or unit you can think of whatever. Okay, 1,000 rupees or 1 unit could be 1 million rupees or whatever. And then 6 units, 5 units, 4 units, and 7. That's their maximum needs. So maximum needs is how much? 11 plus 4, 15 plus 7, 22. But it has only 10 units of resources. Okay. Then let's assume that at certain point in time, this is the state. It has granted resources in this way. Okay. Is it a safe state?
Yes, sir.
It is a safe state, right? Because say for example 2 resources are available here, it can give it to C, and then 4 will be available, it can give it to B. So this these many resources will be available. Okay, so 5 resources will be available and then can give it to A, then 6 resources will be available and then it can give it to this one. So Now, banker will give money to whom? Banker first, if this is a situation, okay, at this point in time, this one, okay, this is the allocation, current allocation, banker will give money first to C and put other process into hold. And when C returns the money or returns the resources, then it will give it to B, and so on and so forth. All right. Okay. All right. So now we can see that if resources are allocated, just forget about. So we were here. Okay. If so, it can, what we have seen here, that is safe. But this sequence is to be used C, then B, and A, and D. And if it gives money to different one, for example, it gives money to B instead of C. Okay, so okay, then it can lead to unsafe state. Even if it gives one resource to B, okay. So for example, it gives, so when it gives to B, then here it will be 2, okay, then it cannot meet the request of any of these processes, right? So now it will get into unsafe state. So banker must give resources only when the system leads to safe state. All right. So that's all. Okay, so now we have studied the banker's algorithm for single type of resource. Now, for example, here units of money or something. Now we can extend this to multiple type of resources. So each process may request multiple type of resources, and total number of resources available. The OS will know, and OS will know what is the maximum need of different type of resources for each process. Based on that, algorithm can be done. Okay, so I will request you to please read from any of the book, banker's algorithm from multiple resources. Very simple, same logic you can apply there, right? Okay, and please go through it and read by yourself. I may ask a question on that, possibly numerical.